the first time, so it's very nice. So my biggest anxiety standing here is the amount of information that we want to convey to you today. So hopefully we can get it all in. So there may be segments that we may, if we're crushed for time, that we need to push through. So we'll start with our title here, Cardioplegia Update, Long-Term Efficacy and Cell Survival. This is pretty much a summation of the work that we've done over the past 3.5, 4 years of looking at single-dose cardioplegic solutions. Our work for over 20 years, Dr. Gunaydin and I working together, we've investigated leukofiltration, blood conservation, volume sequestration, antifibrinolytics, biocompatible coatings, polymers, a full array. Pretty much we spent a lot of time working on modifying extracorporeal circuits. So that body of work, we really pushed the envelope there. So if you're running a circuit that's less than 1,000 mLs, hopefully you're aware of the work that we've done. We went on and we patented most of that work. And the work that we were doing there is that as we were trying to condense the circuitry, we never used the term miniaturization because we never miniaturized anything. We used the manufacturer's products that they provide to us and reducing the prompt. The first publication we had in that was 1998, where we came up with the MASS system, minimized area surface modified technology, and we were altering the hardware to really go ahead and obliterate all the tubing. The next area that we followed up with was the Pinnacle system. But as we were doing that, the dilemma that we had was trying to then go ahead and condense the cardioplegia circuitry. So we modified that and had great success with that, taking a Perfusion pump, coming up with an algorithm, and then trying to create an induction flow rate where we would get the 8 to 13 milliequivalents that we needed to achieve an arrest. So when these ideas of single-dose cardioplegia, for some was a resurgence for Brett Schneider and HDK, we took a step back and we said, well, how should we approach this? We approached this with our first study, which we identified that we would go ahead and we would look at 3 cell culture lines. We would examine L929 myofibroblast. We would look at H9C2s, which is neonatal cardiac myocytes, and also UVEC cells, human umbilical vein endothelial cells. And we'd examine them. We'd go ahead and we would seed them, incubate them, put them under the microscope. We'd go ahead and do a lot of staining and see what our findings would be. So our disclaimer here is we have no conflict of any. We conduct our research out of each of our medical institutions. So I'll give you an outline here. So the areas that we want to cover are a concept of myocardial protection, history, single-dose solutions, research project, our projects. We're going to cover enormously what our experimental stage was and our clinical findings was, and also nuclear imaging. So to get going on this, so basically tongue-in-cheek, when we start everything, we start to do a literature search, and what do we find in the history of our profession? There's about over 400,000 publications that are available to us. Cardioplegia is about 16,000. Recently, the thing that jumps out, if you do the search, is for HTK, there's about 136 publications, and for Del Nido, about 37 recently. So we want to talk about myocardial protection. So, and we can identify some of the pathophysiological effects as a review as we get into this. So. We look at complex interrelated pathologies that we know. So our goal in what we're trying to do as perfusion is to protect that endothelium, protect the myocytes. And there are the injuries that do occur. So we have reperfusion injury and the ischemic injury. In the reperfusion injury, there's the one that we're mostly trying to avoid is the calcium oxygen paradoxes. And we're going to talk about that a little bit. So in 1955, we were given the first definition in the literature of a definition of cardioplegia. It's a series of interactions aimed to limit the iatrogenic injury associated with conducting cardiac surgery with cardiopulmonary bypass. So in what we have to offer, we can do that chemically with hyperthermia. We can use radiologics and hydraulics. So with cardioplegia, it's the broad formulations. We have 2. Right, intracellular formulation, which is a hyperkalemic or a hypernatremic. Ironically enough, depending on which one you're going to choose is which side of the Atlantic Ocean you've been standing on. So when we give the cardioplegia, we're trying to disrupt that myocardial electrical mechanical coupling. And we're trying to make that myocyte refractory to the electrical stimuli. So if we can just go ahead and raise that resting membrane potential from 80 millivolts to 60 millivolts, we were able to do so. So in our armamentarium, what do we have, right? So we each have so many different things. When we had the perfusion school back in New York in the 90s, we sent students out to 16 clinical sites. They all came back with, we tried to do an initial survey, and they came back with 24 recipes. So not every center is going to be dedicated to a single agent. So here, to get into the calcium paradox quickly, because we want to review this to see what we're trying to prevent and what we're chasing here. So some basic science, we'll just look at the structure and function of the heart and the myofibrils with the myocytes. So when we talk about the sarcomeres, and they're the tiny ones, so they're about 1.8 to 2.0 microns. And the preload is that they're going to stretch. They'll stretch up to 2.2 microns, and that length-dependent activation is going to be based upon the affinity for calcium and the increased troponin C. And you can see the Z-band. So the heavy chain that's there is the myosin. We know that's 470,000 Daltons. There's a bucket load of them on each of the filaments, about 300 molecules. And each myosin will contain 2 heads. And then the ATP will be hydrolyzed from there. There's 2 strands then which sits in the alpha helix. And the actin is a globule protein, which is, and I'm going to show you a video which we've created. It's a repeating chain that occurs. And the tropomyosin sits within that alpha helix. So there are 3 components there. We have troponin T, C, and I. The T is going to attach to the tropomyosin. The C is the binding site for the calcium during the excitation contraction. And the I will inhibit the myosin binding to the actin. And there's going to be a conformational change that occurs as the calcium drops onto the troponin, and it's going to be a pullback in the helix, so the myosin can get towards the actin. So here, Peter DeToom, a physiologist up at the University of Illinois, actually published this a couple of years ago in the Journal of Biomechanics, and he describes it almost a spooning effect, where is this just okay? So the spooning effect here is we'll have the calcium to the troponin C is where the calcium is going to raise. The troponin T is inhibiting here for the troponin T, where the calcium is going to lay in sight. The ATP is attached to the myosin. And he describes this as this is spooning into the helix. We actually see it a little bit differently, so we can take a closer look there. So here are your players. We have the myosin complex with the ATPase activation, the actin helix, the tropomyosin, ATP, and the troponin. So hopefully, here's the video that we've. So that video's not working. All that work on that video. So what we're going to have is the sarcoplasmic reticulum is going to drop down this calcium, right? It's going to touch into the troponin. Once it hits the troponin, this is going to roll back to the helix, and the myosin is going to drop into touching the actin. The important thing to know is that as the video would play, it would be in, the video flows this way, but it should be in a repeating fashion. Once the actin, once the myosin touches the actin, you'll see, I had in the video that there was a conformational change here that you can see, is that magnesium would actually fly in here as a dagger and then release the calcium. So that's important. So this is just a highlight. So if we're behind the pump and we're doing all of this trying to maintain homeostasis, I just want to give you an idea is that if we think that we're just going to lay that organ down, an organ that's going to beat 3 billion times in our lifetime and pump about 210 million liters in our lifetime, we need to think a little bit further. So this just gives you an idea of all the receptors that are working through in the kinase change before it even hits the nuclear membrane. and then there's a genetic connection as well. So we can just touch, I have just one slide, but I think, as we know, we need to give credit to these icons that are here just so we go over the history of this, of what we're trying to achieve. So Dr. Bigelow in 1950 came up with the idea of in these canoe-like chambers of putting ice and submerging and getting the core temp down. And then in 1952, Dr. Senning was doing a fibrillatory arrest, but was very concerned about emboli that was occurring. And then Dr. Shumway, in 1959, actually gave us the first publication for selective hypothermia in the heart and anoxic cardiac arrest. And in 59, he had nowhere to publish that journal. He actually ended up publishing in the Journal of Obstetrics and Gynecology. And then Dr. Cooley, who was, in his writings, was of grave concern to that ischemic contracture of understanding that calcium paradox. And then Dr. Bainbridge was for the Plegisol development, and then fellow Bronx, a guy who grew up in the Bronx is Dr. Buckberg, who went on to Ohio State and then became the chairman at UCLA. And he always admitted he was a slow surgeon, and the development of blood cardioplegia. So single-dose solutions, right? So this comes out, and we start to hear about this. And in the formulation, it's 16.3 mLs of mannitol, 4 mLs of magnesium, 13 mLs of potassium, 2 mLs per, 13 mLs of lidocaine, and 13 mLs of sodium bicarbonate. And so the idea that Dr. Del Nido came up with it, that this was going to reduce energy consumption, and it's going to block that calcium flux into the cell. It would also scavenge the hydrogen ions, preserve high-energy phosphate, and promote that anaerobic glycolysis during the myocardial arrest. The biggest concern is it does not keep the heart cold. When we spoke at the CREF meeting with Dr. Del Nido, and we have a photo here coming up, the biggest concern is that he cools every patient to 24 degrees. And in centers that we've gone around and we evaluated people using Del Nido, if you look at the echo probe, just simply look at the temperature on the echo probe, you can see that the heart pretty much is reading 28 to 30 degrees. So that's a concern. So the mix there initially was a 4-to-1 crystalloid with blood, and it was given 20 mLs per kilo at 8 to 12 degrees. It was originally designed for pediatric use, and then it's modified itself over into the adult community. And that's why we had set up our initial study for that. There's 200 different modifications now, but there's actually probably up to 300 modifications of this. Everybody has their own Del Nido cocktail that they're delivering. And the lidocaine dose is very important. So the other side of the single-dose cardioplegias were HTK, which had been around from the 1960s and then used as an organ preservation solution and then made a resurgence. So it works using a sodium depletion of the extracellular space and causing a hyperpolarization of the monocyte membrane, plasma membrane, inducing cardiac arrest in diastole. HTK is the acronym for histidine, tryptophan, ketoglutarate. Histidine is a great alkalizing agent, which will help with acidosis, anaerobic, and long ischemia. Ketoglutarate for ATP production during reperfusion, and tryptophan is a cell stabilizing moment. So when we started on this, we always lay down our checklist, and we talk. We talk to each other every morning, and probably more than any other people in our lives. And we sat down, we had a checklist of what we're going to look like. So the positives here is Del Nido is a pediatric formula for immature heart and low temperatures. HTK, pediatric treatment for adult. 200 modifications, HTK is a single formula. There's satisfactory evidence in pediatric surgery for Del Nido, satisfactory evidence in adult valve surgery for the HTK, coronary distribution retrograde for both, hemodilution transfusion, concern for both. But we're going to show you our clinical studies, and I want to show you some early clinical studies of another group and what their findings were. So the lidocaine dose is a dilemma, because if you're going to then feel that after that initial dose and a longer period of time has gone, you're going to have to go ahead and titrate that. So you don't want to get into the toxic levels with the lidocaine. On the sodium end, which the HTK is the volume, and then we feel that we need to hemoconcentrate to remove that. That's not the case. So there's conflicting data on the limited population on both and limited clinical parameters. And there's no data on long-term outcomes for Del Nido and no data on long-term outcomes for HTK and the cost. So the questions that we have is, which patients should we be using this on? Pediatric adults, which surgeries, pediatric adult valve, adult cabbage, outcomes of myocardial protection, early, perioperative, and late. So the recent research. So we then ahead, right? So the next step is go ahead and go through the current literature and what's laying there for us. So there's always equivalent and early, better outcomes in the conventional techniques in pediatric population. That Dr. Del Nido describes. Mostly equivalent or better early outcome than the conventional techniques in adult surgery. And there's conflicting data on limited adult cabbage population. Very limited parameters were studied, troponin levels, temperatures. And there's no data on the long-term outcomes. So the group from Nashville went ahead and published this paper of, does the type of cardioplegic technique influence hemodilution and transfusion requirements in adult patients undergoing cardiac surgery? The thing almost instinctively is we look here, this jumped out at us. Because that, if you've been doing this a long time, it was you almost had a visceral intrinsic reaction to years back when we had Luca filters and Carmita coated with a Maxima wrapped in a closet with a lock on it, that you would only use those for really, really, really sick people. When we went through the data here, it almost gave us the impression that when there was an urgent case and there were really sick people, that the high percent of the time is that people were reaching for the HTK. Then the other area was, well, what is that concern about the hemodilution? We looked at what their baseline hematocrits were coming into the room and what they were leaving. When you go through that data, if you look at the time after protamine administration, the group that has the greatest fluctuation in crits was the 4-to-1 group. Then further in that study is when you look at the transfusion rates. So the group that received the most crude transfusion rates ended up being the microplegia group. Microplegia group followed by the 4-to-1, followed by the Del Nido, followed by the HTK. So here's our experimental project. So we then started our studies, and this was the first one that we had developed, and I said in the beginning is that we wanted to examine 3 cell lines in doing this. So we needed to create a cell culture model. So we identified that we could use myofibroblasts, cardiac, neonatal cardiac myocytes, and human umbilical vein endothelial cells to examine. We went ahead, and our aim of that project was to single test the single dose cardioplegia solutions and examine the cell viability, the cell integrity versus time, demonstrated long-term myocardial protection. With that, the cell viability, we used the MTT analysis. Now, one surgeon had asked us, I think at the International Valve Society meeting, why don't you use MTS, which will actually save you a step. But when you go to MTS and you're saving yourself that step, when you're dealing with diphenyl tetrazolium bromide solutions, you can get colorimetric interference. So we felt that we would continue to stay with the MTS analysis. Also, we need to underline the answers to the questions, acting better on pediatric, adult, or myocardium itself. So here with the MTS assay, we put them in 8 wells. We seeded them, incubated them, did a baseline, did 2 hours, 6 hours, 24 hours, and 48 hours. And here are our findings for that initial study, is that when we looked at the L929, the fibromyoblast, is on the viability, you can see 2 hours consistent, 6 hours, and after the 24 and the 48, you can see that the HTK in the 48-hour period starts to separate itself from the group. With the UVAC culture, same, everyone's very close, 2 to 6 hours, 24, and at the 48-hour period there as well. And then for the neonatal cardiomyocytes, those cell cultures on viability, consistent and del nido, as he predicted, that's very high. So we did then cytotoxicity studies measuring HDL levels. So we want to measure cell disintegration levels. So higher is not good. So you can see here on the L929, the UVEC, and then on the neonatal cardiomyocytes, the benefits there are in that del nido and the HTK group. So with that, then, the next steps that we do is we do electron microscopy imaging, and we'll do some staining. So we'll use acridine, orange, and propylium iodide in our stainings, and an enormous amount of prep work that goes into this. And you can see, so everything in green, I don't know if you catch those images, it's clear on our laptops, but here it's a little fuzzy. So the green imaging is going to be, anything green fluorescent is going to be viable, and the red-orange is going to be non-viable cells. So it's incredible how poorly the plegisol performs in this upon examination. And you can see the abundance of cells that are viable in the HTK and the del nido. And here on the neocytes, almost identical with the HTK and the del nido settings. So this study then we presented at the Academy meeting back in February, and it was a safety dilemma of long-term protection of del nido, HTK cardioplegia, minimally invasive valve surgery. So we did this prospective cohort study, and we included high-risk patients in EURO scores greater than 5 undergoing primary minimal invasive valve replacements. We used St. Thomas, del nido, and HTK. We then figured that we would go ahead and measure serum syndecan-1 levels when we measured them using the enzyme-linked immunosorbent assay, and taken from a femoral line and from the coronary sinus at the end of bypass. Those are the 2 time intervals that we're going to do. We're also going to take a left ventricular punch biopsy specimen. We'll collect at the end of bypass in each of the cases, and then we're going to go ahead and incubate those cells in a lipopolysaccharide protein with an interleukin-1 beta. And also, we were going to then measure endothelial glycox shedding. So the amount of syndecan level will indicate to us the amount of endothelial glycolyx that was being removed. So those, so the endothelial glycocalyx is a lipoprotein, and if those levels then get high, we know that we're starting to trigger the inflammatory response at a high level. So here were our results for that. There wasn't a significant difference among the groups with respect to the demographic data, BMI, and the change in the troponin levels. The early perioperative data demonstrated that all these 3 types of cardioplegia techniques provided effective clinical outcomes with similar effects in blood biochemical parameters. Cross-cutting times were relatively the same. And you can see the shift in the cell culture where we're starting to have the endothelial glycocalyx levels much higher in the St. Thomas and lower in the HTK. And then here, as we stain them, the viability is the dimmer one. So at the top, you can see the HTK is more viable in that biopsy setting. So then we went ahead and we presented this just at AMSACT last month, and we wanted to measure the impact of the myocardial protection by the single-dose cardioplegic techniques on microvascular integrity in that endothelial glycocalyx and combined to CABG and valve cases. So this prospective study included patients undergoing combined aortic valve replacement who received different cardioplegic solutions. Those levels were measured again by enzyme-linked immunosorbent assay at the times from the arterial line at the end of bypass. We did a right atrial specimen at this time, and the cells were incubated in a lipopolysaccharide solution in a control medium. Again, so here are the results from there, is that you can see we start to see that in the later time interval that the syndecan levels are far less there. In the microscopy imaging here from that right atrial punch, here's the HTK solution. So we're seeing that we're not triggering that inflammatory response. We're not having that shedding occur. And so in our laboratory, we pretty much follow traditional classic translational research, where with that is that you discover a mechanism, you identify a target, you go ahead and do your experiments, you try and come up with a device and then do a clinical trial. What we're finding in these single dose solutions, it's almost a reverse translational type of complex that's coming up, is that you have a clinical observation, you then go ahead and do some experiments, then you have proof of concept, and then there's reiterative steps that follow through that to go ahead and try and identify that. So our projects here is that, so I've run out of time. So I'll turn it over to Dr. Gunaydin. He can finish our clinical setup.
Thank you very much. Now I'm going to go on with the clinical studies we've done on comparison of different cardioplegic solutions. We usually collect data in this hospital I work. It's one of the largest hospitals in Europe, I think #2. So we have a very fairly good clinical load, about doing more than 3,500 cases a year. So when we started doing projects on comparison of cardioplegic solutions, the idea is to set up the clinical setting, because we've done a lot of studies on new techniques in cardiopulmonary bypass before. And when you compare the power analysis, you need like more than maybe 10,000 patients. So it's not a feasible way of doing clinical studies. So we have the idea then to compare the patients with the highest risk group, that you can find some kind of differences in the early period or with a limited number of patients. So in this case, when comparing the cardioplegic solutions, so we set up a protocol to just continue to monitorization of these patients up to 2 months. So that's the way we could try some significantly different results. So when you're comparing the cardioplegic solutions, I need to tell that the beginning of the effect of the custodial or the other Dalnido or some, for example, St. Thomas solutions is different. For example, you see here, so St. Thomas solution is just being started here. This is the intravasal, the blood, the extracellular space, and the heart. So when the heart stops, you see it took about two minutes to stop the heart with St. Thomas solution. And then you now see, again, the same setup. We did this with the experimental techniques on the cells. And again, you see the St. Thomas now. So you see the extracellular space, the potassium, and intercellular space, and the potassium and sodium levels. And so when you just now check for the custodial and the time here, so this time the idea is to diminish the sodium levels in the extracellular space. The HDK does this impact like that. But in this case, we should know that this would take more time compared to St. Thomas or Dalnido to stop the heart. So in order to have an effective result, you should wait at least 5 to 6 minutes before the induction, or all over the induction. Because if you stop it here, now the level is not satisfactory down there. So this is one of the most important points in using those cardioplegic techniques. And now we see, yeah, just talk about the custodial. And now we restart the heart. As you see, this is the reperfusion solution. And the sodium levels are going up and potassium levels are going down. And as you will see, this will take longer time than HDK to restart the heart. The heart doesn't start until now. Yeah. And Now we see the custodial. As you see, the reperfusion acts very quickly, and the heart will start significantly shorter than St. Thomas or than needle. So this is the idea on the molecular phase. And let's go with the clinical experiments that we done. Our idea was to compare the long-term outcome of the clinical results in between different cardioplegic techniques. Because in the early outcome, when you check troponin levels, cross-clamp times, or how many times do you need defibrillation, there is not any possibility to show a clear, significant difference. So that's why we go up further. So we have 4 different groups that we use, very often, and we try to define how we can understand the long-term efficacy of a cardioplegic technique. So we decided that we can check for postoperative tachycardia, bradycardia, some arrhythmia, and some kind of problems of the patients, like shortness of breath, edema, or heart failure. So then we just started using this device. It's called LifeWatch telemetry. So it's a kind of like iPhone-like device. You connect on the patient as we're discharging them. And we have a call center that works for 24 hours, 24/7. So the patient has a kind of simple device with the button. When he or she feels uncomfortable, she presses the button, and this service takes an SMS. And also, there is a continuous documentation and monitorization of the patients with ECG, blood pressure, or anything. So we follow up those patients up to 2 months, the first month and the second month, and we compare the clinical disturbances of those patients. As you see here, these are the groups. So in HDK group was the most satisfactory group in 1 month, and now we have the 2 months results, and these are much more clear in the significant level. So we follow up those patients thoroughly up to 2 months, and HDK group had significantly much better results. And then we go on following a different design with the minimally invasive group, because in especially heart valve surgery, we use those those techniques most often. So in those groups, again, you see the HDK group is the yellow one. So with respect to tachycardia, bradycardia, and other patient kind of symptoms, the HDK was significantly much better than the other groups. So we also studied minimally invasive valve compared, so all types of surgeries at the same time with very long following up to 3 months. Even in 3 months, we just set up the same follow-up parameters. And after all those follow-up, in the early postoperative period, we don't see any clinical differences. So it's very easy to follow up those patients up to 1 week. But in the long term, for example, after 3 months, it still states that the AFib episode is much more significantly higher in the needle group. So considering all of these, now we're maintaining a new study for the financial outcome of those. So when you just record up to 3 months and just check for the rehospitalization rates or some additional drugs you use, some additional activities, so it really is very effective with respect to HDK follow-up of the patients. So, and another criticism over the single-dose technique was the hemodilution. So when you use St. Thomas or microcardioplegia, and when you use single dose, they just give 2 liters at the same time. The major criticism were the hemodilution. So now we just designed a clinical study to compare the hemodilution levels in different cardioplegic techniques. So about 300 patients in each group. And the primary endpoint was the transfusion rate, and the secondary endpoint was the hematocrit change before and after surgery. So we use all parameters with cerebral oximetry and TAG to compare the platelet function or the hemodilution level. But when we compare the total volume, these are the complex cabbage plus valve, or it's a long-lasting operations. So in St. Thomas group, the total volume, and when you see the total volumes, they are significantly not different, so very much close. And we always use ultrafiltration at the end of the operation for single-dose techniques until the hematocrit of 27. So the ultrafiltration rate was, again, very much same. We didn't demonstrate any clinical difference. And when you look at the clinically, there's not any difference in between blood transfusion or arrhythmia or anything else. So the secondary endpoint was the hematocrit change. So as you see, different groups, there's not any significant change when you use ultrafiltration at the end of the operation and when it's a long-lasting operation. No worries about the hemodilution in those all groups. And this was the study we also presented in last year in ISMICS meeting for minimally invasive mitral surgery. It's also a challenging surgery, you know, that had 45 to 50 patients in each group, again, in the long-term follow-up monitorization. And this time in the minimally invasive group, the nido was really comparatively significantly worse with respect to other groups, even with respect to St. Thomas, according to the incidence of tachycardia, bradycardia, AFib episodes especially. And now this year, we're going to present another study in ISMICS next month in New York. We compared this time the hemodilution levels, and we did not demonstrate any significant difference in all those groups. And we also did some nuclear imaging testing. So these tests are done to follow up of the patients with the heart transplants. Because when you do heart transplant, you damage the innervation status of the heart. So the iodine MIBG is a tracer that shows you the innervation capacity of the heart. So the transplant surgeons follow up the patients with the MIBG data, and when they have a satisfactory innervation data, they say, okay, this transplant would work. So this is a very precise demonstration of the protection of the heart function. So these two groups, the Dalnido is upside and the HTK on the down. So this is the MIBG in the preoperative level. This is the perfusion. So this is the heart. So this should be all full in order to show you a full functioning, excellent heart. So this is before and this is after. The first one is innervation. The second one is perfusion. So if there is a mismatch in between innervation and perfusion, that means when a point of heart is perfused, but not innervation is not complete, you always see arrhythmia. So this is a rule. And this is the HTK protection. As you see, at the end of the 1 month, so HTK protection of the heart is significantly much better than NIDO, and also the innervation would go up to 3 months, maybe 6 months sometimes after cabbage operations, is still at the end of 1 month significantly better than NIDO group. And now we have ongoing studies, especially on, again, on the hemodilution. You know, there is a new concept called the aquaporins as a very newly sub-element of the cell wall, so that controls the hemodilution status of the here, the aquaproteins and aquaporin water channels. So when the patient is really very much loaded with some kind of fluid injection, you can see disturbances in the aquaporin level, even in the microscopic level. So now we're trying to demonstrate different cardioplegic techniques with different aquaporin outcomes. So we have some different dyes and like that. So this is, for example, an over-transfused patient. You see the endothelium here, this much. And this is a normal patient with the same magnification. This is the endothelium of a normal patient, and this is the patient with the overtransfusion. And also we're working on some nanoparticles to decrease the volume of the cardioplegia we are administering. This is another project ongoing because when you use nanoparticles and you load the cardioplegia on those nanoparticles, you can decrease the volume so you don't have any hemodilution problem at the end. So as a conclusion, myocardial preservation is still a concept without very clear and specific clinical science. So it's much difficult to set up a clinical study to demonstrate differences clearly in a limited population or looking for a short time in the postoperative period. So we're trying to set up new models to study those in popular cardioplegic techniques and to show some differences, benefits, or some disadvantages. Thank you very much.